Alright, subscribers, welcome back to another episode of Science with Sirback. Today what we're going to be talking about is Chemistry 1, Section 22.2, and this is going to deal with cyclic organic compounds. Now before we get into the details of notes, here's a few objectives that I want you to be able to accomplish by the end of this video. Number 1, name a cyclic alkane by examining its structure. Objective 2, draw the structure of a cyclic alkane given its name. Objective 3, describe the properties of alkanes. And the fourth and final objective is distinguish between saturated and unsaturated hydrocarbons. So, we left off naming and drawing alkanes in the last section, and now we pick back up with this particular portion of organic chemistry. And so we have this business of a cyclic organic compound. Now, a cyclic hydrocarbon is just going to be defined as an organic compound that contains a hydrocarbon ring. So we mentioned in the last section that carbon can have 4 attachments or 4 different covalent bonds, where it could attach to another carbon, and that carbon could attach to a carbon, and that carbon could attach to carbon, and so on and so forth. So it was already complex when those carbons could attach to each other, and now we bring in this ring structure, and that's really what that cyclic definition is. And so because we bring in this ring structure, this is one of the reasons there's so much variety in organic compounds. So what happens here is this: how we identify or how we go through a cyclic hydrocarbon is we are going to indicate that a hydrocarbon has a ring by using the prefix cyclo. If you see cyclo in front of the longest chain carbon, then that means that is a ring structure. All of those carbons are connected together. And I just want to make clear this. When I talk about a ring structure or cyclic, I can use those terms interchangeably. What I'm talking about is all of the carbons are connected together. And so hopefully this will make a little bit more sense as we transition from this generic definition of a cyclic organic compound to specifically our cycloalkenes, and that's the next thing that we will be talking about. So cycloalkanes, what these are, they are defined as cyclic hydrocarbons with only single bonds. So because all of these carbons in a cyclic structure have to connect together, there has to be at least 3 or more carbons in a cycloalkene or in a general cyclic structure. Now the best way to go through this is to actually see some examples here. So we start out here with cyclopropane. Again, cyclo, that prefix, means the carbons in that longest chain are connected together in that ring structure. And then propane, if you remember back to the chart, propane means 3 or has 3 carbons in that longest chain. Now, a couple of things as cyclopropane here. This is going to be the smallest cycloalkane. And how cyclopropane looks is if we draw, it almost looks like a triangle. And the triangle, each vertex of the triangle, so points 1, 2, and 3, represents a carbon. So if you want to imagine this, and sometimes I go ahead and do this, at each vertex, so at each point in our cyclic structure, there is a carbon. So sometimes I go ahead and I just insert these carbons so I don't confuse myself about where those carbons are. And so that is how it looks. It forms these types of shapes when they form this cyclic hydrocarbon. Now, cyclopropane was once used as an anesthetic or something to do some numbing of that particular area. And then another really common example of a cycloalkane is a cyclohexane. Again, cyclo means it is in a circle, or all those carbons are connected together, and hexane means the number 6. So what this looks like here is this. It has a 6-sided ring structure that looks like this. And so that would be our cyclohexane. And with this here, again, each of the points of this structure represents we have a carbon. Now, the one thing that I'm not drawing in is those hydrogens. Remember, each carbon wants no more, no less than 4 connections, whether that's to another carbon or whether that's to another hydrogen. It wants 4 connections because it has those 4 valence electrons and wants to form those covalent bonds in those locations. Now, a couple of points here, side notes about cyclohexane, is it's obtained from petroleum, and then it's used in paint and varnish, and this helps remove, or paint and varnish removers from those oils that make perfume. So those are those points there. Now, I've already started to show you some of the ways that we can represent cycloalkenes, and it's really important, again, to identify the structure and how we represent it. So on the next page here, what we do, just like we did in section 1, is we are going to go over each of these particular structures. Now, a condensed structural formula shows both the carbon and hydrogen atoms in the hydrocarbon. So an example of this would be pentane. How about cyclopentane? So in cyclopentane, again, cyclo means it's in a ring structure. Pentane means there is 5 carbons. So it would show both the carbon and the hydrogen atoms, and so it would look like this. We'd have CH2 connected to another CH2. And then down below here, this would be connected to another CH2, connected to another CH2, and then these last carbons would be connected together. That's how that condensed structural formula would look. Now, a skeletal structure is going to show only the carbon atoms. What we assume is this: the hydrogen atoms are, again, assumed in this particular structure. So again, the best way to go through this is our example cyclopentane. Again, same thing, same example that we did up above for the condensed structural formula, but for the skeletal structure, we're only going to show those carbons. And we assume that each of these carbons has the appropriate number of hydrogens. So again, we have the 5 carbons from the pentane portion of this name, and we assume that those hydrogens are still there to make a total of 4 connections, or make a total of 4 covalent bonds with each of those carbons. Now, the most common and the most thing that you'll see, or most structure that you'll see, is a line structure. So a line structure is only going to show the carbon-carbon bonds with lines. There's going to be no C's, and so what we do, the carbons are going to be understood to be attached at each vertex of the structure. And then also, in addition, we say, or we assume, that the hydrogens are going to occupy the remaining bonding positions unless you have those attached groups, or those substituents, as we like to call those. So again, I use cyclopentane as our example here for our line structure. So again, cyclopentane Pentane, the same type of structure that we've drawn in the previous two examples. I'm running out of room, so I'm going to write it on the right-hand side here. But it would look like this. It would just almost look like a geometric shape, and each of these vertexes, like I've said on the other pages, represent a place where we have a carbon-carbon bond. Now, the hydrogens, again, are assumed to occupy each of those positions until each of those carbons occupy or have a total of 4 attachments. And that's because of those 4 valence electrons. So now what I want to do is I want to shift gears. I want to give you the steps to be able to name our cyclic organic compounds, or at least our cyclo alkanes. So we start out here with our steps. The first step is to name the ring, or identify the ring as the parent chain. And so however many carbons are in that ring structure becomes your parent chain name. The next step is numbering that bonded to the attached group or substituent. Remember, these cyclic structures have no end, so we have to start our numbering wherever there is an attached particular group. So in the case where there are multiple attached groups in a cyclic structure, what we are going to do is we are going to number in the direction that gives the lowest possible numbers for those substitutes or attached groups. Those things can be used interchangeably. So the name of the game is to get the lowest possible numbers possible. Now the final step here, or the final note of this naming cyclic organic compounds, is this. If only one group is attached to the ring, no numbering is necessary. So again, reference these steps as we go through this particular process, and this will help name the structures that we go over. So we start out here with a structure that is already drawn, and we have this particular structure. The first thing that we do is we count the number of carbons in our longest chain. Now, for a cyclic structure, that's really nice and convenient because the longest chain, no matter what, is going to be however many carbons are in this ring structure. So remember, each vertex represents a carbon. So the number of carbons in the longest chain carbons, which again is just the number of carbons in the ringed structure, is just going to be a simple count. Now, each vertex represents a carbon, so we have carbon 1, number 2, 3, 4, 5, and 6. So there are 6 carbons in that longest chain carbon because it's the ring structure. And then if you look back to section 1, this chart is really important here. We find 6. The name for that is hexane. But what I want you to do is give a little bit of room over here, because after we write hexane that represents 6, we need to indicate that these carbons are all connected together in a ring structure. So what we have to do, we have to add that prefix of cyclo. So right here, our parent chain becomes cyclohexane. Now that's what we'll put at the end, just like we did for section 1 when we named those branch chain alkanes. Now what we have to do, the second step, very important here, is we need to number it so that each of the attached branches give or have the lowest number. So what we have to do, something that you have to do, is you have to number it so that the groups get the lowest number. So if you have a group, just go ahead and start your numbering at one of these groups. I'm going to start with this a group right here at the top right. And so if this is carbon 1, my next group occurs at carbon 2. And then I have carbon 3. My third and final group occurs at carbon 4. So keep the numbers 1, 2, and 4 in mind. And then I'd have carbon 5 and carbon 6. Now, I know I have to start at the lowest, or the lowest number needs to start with that attached group. So what if I start here again, and this time I go backwards? I want to see if I can get lower numbers than 1, 2, and 4. So I have carbon 1, 2, 3, 4, 5, and 6. So I can get carbons 1, 4, and 6. And ask yourself, is that lower than 1, 2, and 4? Well, the answer is no. So what I have to do, the first way I showed you to number it has to be correct, because each of the attached groups has to have the lowest possible numbers. So what I do, I always like to identify each of those carbons so I know what I'm talking about. I usually do it in a different colored pen or pencil. And so carbon 1, I said, had to be this group right in the upper right. Then carbon 2, carbon 3, carbon 4, carbon 5, and carbon 6. Now, you can double check my method here, but there should be no other way to get the lowest possible numbers on all 3 of these attachments. So now what we need to do is we need to name these attachments. So I start out here with my first attachment at carbon number 1. Again, I like to isolate it when I name this, so I identify here that at carbon 1, so at carbon number 1, I have an attached CH3 group. So there is this attached CH3 group. And so what that means for us is that we have something with 1 carbon. And again, if you get out this handy dandy chart, something with 1 carbon is going to be given the name methane. Now, we don't name it methane. We can't have that ANE ending. So what we have to do is we have to chop off the ANE ending, because it's a branch, and put on YL. Now, we go to the next attached group, which it occurs at carbon number 2. So at carbon number 2, we again see that we have a CH3 group. Now, I just got done showing you that chart that an attached CH3 group was given the name on our chart as methane. But because it is an attached group, we cannot have the ANE ending, and so we have to change it once again to YL. And so we get to our final attached group, which occurs over here on carbon number 4. We have again an attached CH3 group. So at carbon number 4, we have an attached CH3 group. Again, CH3 is methane, but we cannot have ANE ending because this is an attached group, or what the textbook likes to call it, a substitutant. So we have to change it to YL. Now we've identified all the attached groups, and we can go ahead, we can name our particular cyclic structure. So we always start with the attached groups. And so remember, back to that branch chain carbon, we always start with the alphabetical order, or the attached group that appears first in the alphabet. And if you look closely, all of these things are methyl attached groups. So what that means for us is that methyl is bound to be first because that is our only one. The other thing to remember is that we have to identify where each of these attached methyl groups are. So because these are all methyl groups, we start out by listing out the numbers right at the start of the particular naming protocol here. So all of these attached groups occurs at carbons 1, 2, and 4 respectively. So how we start out the name is carbon 1, 2, 4, and then we put a dash. Now, all of these are the same attached groups. So, because there is 3 of these same attached groups, we designate a prefix of tri. So that says there is 3 of the attached same groups, and then we just put the word methyl to indicate what particular group we have in this case, this scenario here. So we have 1, 2, 4 trimethyl, and then at the end of it, we just attached that name of the parent chain that we started with. So at the end, smushed right to the end of it, we get cyclohexane. So the name, the IUPAC, International Union of Pure and Applied Chemistry name for this substance up above is 1,2,4 trimethyl cyclohexane. It's a mouthful, but again, if you follow the steps, step by step, you'll be fine and be able to name these organic compounds. So now, let's go backwards. Let's go from a name to a structure that is drawn. So what we do here is this. We're going to break it down, and again, it's going to be a cyclic structure. One of two things I tell you in the problem, and then 2, right here, you see this term cyclopentane. So whenever you get to a name, the most important part when you go from name to drawing is how many carbons are in that longest chain. Cyclo means that you are in a ring structure, so all of the carbons are connected together. And then pentane, if you use your chart, that means that we have 5 carbons. That's where pentane comes from. So what I like to do, we know that all of these carbons will be connected together in a circle, and there's going to be 5 of them. So what I do here, I have to have 5 carbons connected together. So I immediately draw my particular carbon. So I have carbon 1, I draw the second carbon, the third carbon, the fourth carbon, and the fifth carbon. Now, I don't put any attachments, I don't put any H's quite yet. All I do is I connect these, and give yourself a little space here because, yes, we are eventually going to have to add in H's, and we're eventually going to have to add in these particular attached groups. So, the next thing is numbering our particular attachments, or our particular ring structure. The nice thing about being able to draw our own structure is we can number it however we want. So I usually start here at the top with carbon 1, carbon 2, carbon 3, carbon 4, and carbon 5. Again, those are just markings I like to indicate to help draw this particular structure. And then what we do here is we go step by step and we identify what each attached group is, and we put that attachment on that specific location. So the first attachment, I always just go right to left. The first attachment is a 1-ethyl. And so a 1-ethyl, it means at carbon number 1, we have an ethyl group. So what we do here, remember the ethyl, the YL, was changed from ANE. So on our attached group, we have ethane. Ethane means that there's 2 carbons. So what I do, a little side note here, at carbon number 1, there's 2 C's, or there's 2 carbons. So what I do initially here is I draw carbon and my second attached carbon. So right there I have my 2 attached carbons at carbon number 1. Now I move to my remaining attached group, which is 3-propyl. Now, running out a little bit of a room here, but at 3-propyl, what this means is at carbon number 3, we have a propyl group. Now again, the YL ending was changed from ANE. So if we look on our sheet here, we have our propane, which indicates that there's 3 carbons. So again, I like to note that before I write it. So at carbon 3, there is a 3C attachments. And so what I do here is I just draw carbon, carbon, and my 3rd carbon attached at carbon number 3. Now what I've done, or now what I do is, since I've named all the groups, I've drawn my cyclic structure, I now go back and I add my H's. Now, it does not matter if you add the H's to the right or to the left. And so what I do here is I'm going to start up in the very top portion of my problem here, and I have this carbon from my 1-ethyl group. And this carbon has 1 attachment. It needs 3 more, so that means it gets 3 H's. This carbon here in the middle has 2 attachments from those covalent bonds. It needs 2 more to get to 4, so I add H2. This carbon, carbon number 1, has 1, 2, 3 attachments, so it needs 1 more to get to 4, and so I add 1 H to get it to 4. Carbon number 2, it has 1, 2 attachments. It needs 2 more to get to 4, so I add an H2. Carbon down here, number 3, has 1, 2, 3 attachments, so it only needs 1 H to get to 4. This carbon in the middle has 1, 2 attachments. It needs 2 more to get to 4. Same thing with this carbon here out towards the middle right. And then the carbon on the end only has 1 attachment. It needs 3 hydrogens to get to 4 total attachments. We keep moving along here. Carbon number 4 has 1, 2 attachments to it. It needs 2 more to get to 4. So we end up with CH2. And then this carbon here, carbon number 5, has 2 attachments. Now, because I put the numbering of 5, I don't want to squeeze that H in. So it's okay to write this H out to the left, which is what I'm going to do. So again, it has 2 attachments. It needs 2 H's to get to 4 total attachments. So right there, this is our drawn structure. And it's the structural formula here of 1-ethyl, 3-propyl cyclopentane. All right, so we've drawn one. We've named one from a drawing for our cyclic alkane, or cyclo alkanes. And now we can shift gears a little bit, and we can talk about the properties overall of alkanes. So the first property of our alkanes is this. The polarity of alkanes. Number 1, they are nonpolar because the electronegativity difference between carbon and hydrogen is very, very small. What this means is that because our electronegativity difference is so small that the carbon-hydrogen bond is nonpolar, which results in the overall polarity of the molecule to be nonpolar. We shift gears here to the boiling and melting points. So for alkanes, they are going to have a low melting and boiling points because there is little intermolecular attraction between molecules in alkanes. And this is from a result of these alkanes having small intermolecular attractions. Another property that alkanes have is their immiscibility in water. Now, if something's immiscible there, that means it cannot dissolve with water. It separates out into two different phases. So alkanes are going to only dissolve into nonpolar substances. The final property, and I saved a whole sheet of paper for it, the final property of alkanes is these chemical properties, or their chemical reactivity. So we shift gears here a little bit. We're still talking about alkanes in general here, but our alkanes, the chemical properties is this. Number one, they're going to have a low reactivity. So one of the main reasons that alkanes are going to have a low activity is that they're connected by nonpolar bonds and have no charge. So remember that polarity plays a major factor into chemical properties, and this business about a charge. Remember, ionic substances transfer that electron, and that results in most of the time a chemical reaction. Well, alkanes don't have that, so there's no capability of them being able to produce that or go through a chemical reaction. Now, for a reaction to occur, there must be a reactant with a full electric charge that is attracted to the reactant with the opposite charge, or a reactant with a partial charge is attracted to another reactant with the opposite charge. So again, there is that reminder written out that to have a chemical reaction, we have to have that electrostatic charge and that electrostatic interaction of some sort, which the alkanes are lacking because they have a nonpolar molecule, and then obviously they don't have a charge like an ion would. All right, so this concludes section 2 of our Intro to Organic Chemistry chapter. I hope you have enjoyed this particular video, and as always, if you have enjoyed, make sure you subscribe.